deployed and it serves traffic. That's what we need to build in the end. There's more than that. Okay, this is the main thing. So bottom line, what needs to happen here? Like before we go into this implementation, generally let's see what happens, right? Let's say if you write something in Go or Python or Node.js, you use some web framework. I'm talking about APIs here. You would write the functions, you would write middlewares, you would have a containerized Docker thing ready, and then you would deploy it as a pod on a cluster or as something on a server, right? So that's what needs to happen. And once deployed, you probably have Nginx or Istio or something in front of it, which will, proxy your request, do authentication, etc. So that is what we need to abstract away in this platform. So you edit code, this is a new domain thing, by the way. You build, it spawns up resources for you based on traffic, by the way, that's another thing. It shouldn't always be running for every function, otherwise it will be very expensive. And you route traffic everywhere. That's the problem. Alright, so why use Go for this? Okay. So so I mean the entire cloud ecosystem, right? I mean, if you just look at this, we have Kubernetes, we have Helm, we have Buffer Broker, we have Key Value Store, OT, if you have heard. Git is essentially an optimized, like open source GitHub implementation, including actions. So you have that. You have amazing database abstractions. This equals C logo here, it's not showing up because it's white, but anyway. Then database operators. The entire thing is built in Go. So why not build RT in Go? And actually, it drops really well. All of these have good client library. Yeah. Okay, so this is the overall architecture. There are 4 components that come into this picture. One is the operator, gateway, ingester, and runtime. We'll get back to this diagram probably later in the Q&A section. We'll look at one by one. And then we also have some other dependencies that are included in the chart. So you don't need to deploy your own database, your lots of etc. So yeah, I'll just give one-liner description of what these are. So operator is the main thing. It's the magic, which basically takes your code and runs pods for that only when needed, and does cleanup. When there's no traffic happening on your request, it should kill the pod and get out. That's what the operator does. That's the main thing. Gateway is essentially just Nginx, Istio, whatever you use, and it basically lets you do rate limiting and other stuff. Okay. Ingester and runtime, so we can get into the next steps. Yeah. Next. Okay. So play the video. Yeah. So this is like a quick demo. So let's start with the control plane, which is the UI that you would get. I think it's not clear. So yeah, this is the UI. This entire thing is Go, by the way. There's no React here, even though AI was used for the front end, it's not React. So it's Go template and server-side template. So this is just taking care of the identity, create projects, and it also interacts with the VCS backend. So as I mentioned, the first step is you edit code and you basically save that code in order to run it later. So that's what this lets you do. When you write something, when you create a project here, it essentially creates a Git repo. So initial plan was to just use GitHub as a backend, but I ended up shipping everything along with it. The reason being I developed a Mac. So if you build something in GitHub Actions, it would be x86, and it wouldn't run on Mac. That's the only reason I started doing it. But yeah, that's the log.
Sorry, not GitHub, because for x86, where do you
yeah.
What do you use for that?
I use Git. Can you go back to the
GitHub thing? Sir, the open source GitHub you're talking about?
No. The code base of litefunctions is in GitHub only. I meant like the function code, right? With the lambda function that I'm writing, that also has to go to some GitHub from here, and it uses the actions of that provider from build to build the container images. So initially I did with GitHub, but the issue was Mac and ARM and x86, so I just had everything local. So that. Okay, now let's go. Okay, this is just a quick intro on the auth here. So instead of having to use a password and decrypt and all of that stuff, it's using, this is recent, like last 3-4 years people have been using passkeys. So there's a really good Go library called Webauthn Go, which takes care of all of the, all of the attestation and all of the things that Webauthn needs. Bottom line, what happens is, you have these two interfaces. Passkey store is where you get the username and use the JavaScript library or the Go Webauthn library to get the credential, which is essentially some binary data. It's like a certificate. which you store in the database, right? And then there's update credential, session, get session. So bottom line, can you go to pseudocode here? Yeah. Bottom line, this is what happens. When we do begin registration, so browsers have built-in functionality to invoke the Apple keychain or fingerprint or whatever. And then you get this challenge, right? Which go upon and it processes it does something called attestation, and then in the end we get a credential which is stored in the database, and then we can verify it. So I prefer to use this because then again there's nothing important in the database as such, because the actual private key is local. So it's like a new way of doing work. So just wanted to share some light on that. Yeah, next. Okay. This is again like this. I want to add something. This is the database part. So SQL C is, in my opinion, I think it's the best database abstraction. I worked with raw SQL, PHP, Django, ORM. I've worked with all sorts of abstractions with database, even Rust SQLX. SQL C in Go is literally like you write DDL and DML SQL files. You just give it some annotations like this: insert into query, has a name, create project. That will give you a create project function in Go. So it takes care of the adapter layer completely. It takes care of type checking, it takes care of SQL injection, everything, right? So especially in AI era, all you should do is have it generate the schema, have it generate the SQL, run the SQL C generate command, you have your database layer done, right? And most of it is type safe, most of it is deterministic. So you're not relying on AI to do any of the critical stuff with the database. So that's I just wanted to share some light on that. Yeah.
So it's like why?
It's not like ORM. So ORM, what happens is when I do like let's say users.objects.get in Django, right? It will try to convert it to a list query and it will do some abstraction on top. What this does is you start with a SQL query, you write a SQL query, and it will generate the Go function. Yeah, it's sort of the other way.
Like save.
Yeah. Correct. So you can control exactly what query is happening. Because the biggest issue with ORM is the query is generated, you don't really have control on it. It could be some crazy complicated query. And the second thing is sometimes what happens is things like pagination, right? So in Django, it basically loads everything in memory and then does pagination in memory. You don't have control on those things. Here you can just have another select query with the limit query, and that can be a paginated function. So you have like more control on what happens behind the scenes. Yeah, so that is CQC. Alright. This is the fun part. So I think there's a demo after this. Can you go to the next slide? Is there a video? It's okay. So when you go to the thing and you create a function, essentially what happens is there must be a video somewhere as well. You can create a function, you select a language, and you write your logic, your function logic. And when you save, that essentially gets committed into the Git repo of your project. So let's say I create a project called proj1 and live functions, and you write a function, it creates a myfunction.go or myfunction.py file in the repo. So this integration with Git is where I'm using this library called BeliefS Git. So originally my idea was to use libgit2. That's a very popular library to interact with Git. It has bindings for Go, every other language. I used it before in Rust and Python. But in Go, I found a pure Go implementation, and I chose to go with it especially because of one reason, which is it doesn't depend on any C bindings. So when you build a Docker image, you can just build the Go image of that. So that's why I chose to use this. And the other interesting thing here is the storage, if you see, is an MB storage. So when you clone the repo, when you write something to it, when you commit something to it, you are not dealing with the file system at all, which gives you security benefits. You don't have to like, read only file system, permissions, issues, all those are gone. And the other thing is, it's in this memory. You can have it be like around a mutex, you can have it shared across coroutines, you can have performance benefits like that. Although I didn't do that right now. But yeah. So essentially it creates a repo, adds a repo, any sort of interaction that happens through Git happens through this. And then of course there's a PCS vendor interface to interact with GitHub. So that's how that works. Okay. Alright, yeah, this is the vendor interface. So you have certain things that can't be done with Git command, where you actually need to interact with the vendor, like create a new repo, add a webhook. So it's like, how many of you here have worked with CIC, Jenkins actions, you have it. So when you push something or when you merge a PR, it triggers a Jenkins pipeline through a webhook. It's the exact same here. When I save something, write function, it saves in the repo, that triggers webhook, which builds the artifact. So you need a webhook to be added, you need a workflow to be added, which is GitHub Actions. So unlike our code-based repos, we control the actions we write. Here, the actions has to be just added automatically when the project is created. All of that is programmatic. Right? So yeah, we create that, and then we just have like a builder pattern to get the right vendor object. Okay, ingesture is, yeah, I think this is a very common pattern. So if your company is moving from Python to Go or something, this is the first place we look at generally, right? Because the HTTP layer is where most other languages struggle, especially the dynamic ones. So what people generally do is you put a GIN server, you put a net HTTP server, which just takes requests and just puts it somewhere, just dumb HTTP server, which improves the ingestion rate by a lot. So I will start with that, straightforward. It's a simple server which takes in requests and puts it in max, which is my pub proper. And then, so any pod that is spun up, right? Let's say product, basket, these are functions. So each of these are listening on a particular subject in the broker. So whenever something is produced, they will get the message, and you can even do things like retries and all those things. But we'll come back to, there's another thing I did for some cases, I'm just directly invoking those issues. Because there are certain framework abstractions that go away when you introduce a binary bytes layer. So yeah, this is the error. Alright, so yeah, essentially all it's doing is producing the messages to the broker or calling the HTTP. That is what it is for us. Again, the QR codes here linked to the exact file on GitHub, so if you use to that. Okay, so the function code itself, right? When I create a function in litefunctions, this is what the code looks like. So you have two kinds of invocations, sync and async. Sync is basically identical to the normal API you can write. So in Go it looks like the response writer and request. In Python it's a fast API function. So it's a framework that we are used to use. Right? So I just have this and I write this. This is one of the main reasons why I had to do the direct call in the previous example. Because the original plan was to use PubSub for everything. But then Go is still okay, it's still pretty low level, it's still bytes. But other languages like Rust, it has extractors, Python has the pedantic serializers, it has lots of abstractions. So I would have to essentially implement HTTP over NATs, which is a whole other project on its own. So I just started invoking it. So yeah, this is the same thing, where you just write stuff. And then the next one, if you see, is the, okay, there's a demo of this, let's play it. Next slide is apologies for the dark. Oh, it's just a photo. Okay, let's just zoom in. So yeah, this is just an API, the same as Lambda, right? So once you create a function, you get an endpoint, and it has an inbuilt Postman kind of UI, and it's simply, and it's just a photo. Yeah, this is it. Okay, let's go through this. 40 seconds. So yeah, you create the function. I put some name. Maybe speed run it a little bit if things seem so. But yeah. So this is a typical response writer request, normal API code you write. Just change the name to Gopher here, I save it. And I have this function. And now if I look at the endpoint, it's a get request by default. These things are not used here, it's a future plan where you can change the gateway. And if you look at AT, which is again running locally, zero domain, it's litefunctions of AT. And it started a build for that function, right? So yeah, I think that's it. So right? Yes. So once the build is done, I think we'll get to the other thing is async. So in async flow, we can be a little more low level because there are no good, like other than the Django kind of world. The framework for async stuff is like not very widely established. So I just chose to have a straightforward input channel, output channel, where you just get a channel, whatever people send to the WebSocket connection, you get as bytes in this channel, and whatever you write back is going to go out to the WebSocket. So that is the idea with async, right? Chunks arrive, you write, and WebSocket is essentially the protocol the client is talking with. So I have some images, but the previous one was like a waiter serving a dish, and this is the sushi conveyor belt just to show channel analogy. Okay, and there's a demo for this also after this. Right? I think this is longer. Yeah, this is longer. We might have to speed it up.
section you can tell me.
Done. Okay. Okay. Cool. So yeah. So now see, before writing the code, I'll probably change it to basic. Yeah. So what this does is changes the response writer's boilerplate to the input-output channel case. And all I have here is I'm pretty not visible probably. It's just a function which is returning a random word. These are like one-piece characters, goofy sort of. And then it's been called the below place, and it writes those names to the channel. I think I will probably store it that. Yeah. And by the way, this editor supports the emotions and all. Nice piece there. Cool. So yeah, so I create straw hats with the async function. So what happened here is it triggered a pipeline for that again. There was this bug with the redirect, so I changed it. Yeah. So as you see, it started a build go. By the way, one quick note about the pipeline while it's building. So it has all these steps, right? Build go, build trust, build pipeline. So the repo which is used by litefunctions programmatically, it's nothing but it's like it has folders for various languages. And under that it has like .go, .python files. That's it, right? So it initially detects which file is changed, which directory, and it triggers the right pipeline. Yeah. So the build looks like it's almost done. And so yeah, it's successful. And now we can probably look at the socket connection. So again, it's like a Postman like UI. This front end is all AI, but again, there's no React involved in it. It's pure. Cool. So I just send some dummy data, and I just get issued straw hats in the response. So this is like imagine if I'm at a startup and I just want to build a WebSocket connection. Freshers generally suffer with how do I build it, because in Go itself there are various ways. I forgot the name of the framework. It has a different abstraction. Then Django, Spring Boot, they've started away even more. Socket.io makes it very complicated. In the end, it's just bytes and bytes. Right? So I just kept the interface very simple, so people can just build a socket. Cool. That is it. We can move to the next one. Okay. Now a little more on the runtime. So we looked at the pipeline earlier, where it has the various file detections in the pipeline. Cool. So one advantage we have is static runtimes, as in static languages like Rust, Go, and Planet-OS, Zig in the future, and Java. So these languages, mainly the good thing is you get binaries. You already have there's a concept of packaging it already in the language. So you can have like a static compiler and a compiled binary. So your Docker image is very simple, right? In the end, you have from scratch. There's probably a build step before this, and you copy the binary into your image. So the image is very small, like 12 MB, 20 MB layers, and then it makes it very easy to spin up the pods. Because the biggest delay when you spin up pods is image pool, generally, right? So a Python image, if not distroless, would be 1 GB, 1.5 GB. Even with distroless, it's 500 MB, 400 MB. But these ones are like 40 MB, 30 MB. You can even bring it down with distroless to even more, right? So that is an advantage of static languages here. And because of this advantage, I chose to go with one pod per function. Straight away, right? So they can scale independently. Whereas the dynamic one will not do. And a few things. So Go max procs is something that was changed in so earlier, what used to happen is so Go has this thing called max procs, which essentially lets it decide how many physical processors to start. I think probably the scheduler talk will shed more light on this. So essentially, Go routines are both parallelism and concurrency. So to decide how many actual workers to start, it detects from the OS generally. But in K8s, when you run a pod, the detection is not accurate. So that had issues. So Go max procs had default, that changed recently. So if you're using before Go 1.22, you should probably set this to the number of cores that you're using. The other thing is what I mentioned earlier, liquid to Go, Git, crypto. So anything that invokes C. So how many of you here write Python? Right? So if you looked at Python libraries, they are called to C, right? Very few Python libraries are pure Python, right? So all of the OpenSSL stuff, all of the encryption stuff, all of the Git stuff, these are all called to C libraries. That makes like Dockerization necessary, that makes all these dependencies necessary, because it's like if you're running it locally, you need to apt install something, for example, right? So what this is doing is, what Go generally I've noticed in Go community, more so than even Rust, is that there is a very There's importance placed on having pure Go libraries that are really good, so you don't have to depend on the C stuff. So that's why I can use Scratch as the base image and just use the Python, right? Which is an amazing thing with Go. Again, why it's more suited for inference stuff, because it has like TLS built into the language is something very unique to Go. Like at the maturity that it's at, something very unique to Go. Even Rust is LS is not that mature compared to Go. So yeah, that is about static runtime. Dynamic runtimes are very similar, but the big issue is you have to install requirements. Those requirements will have some app dependencies. Like if you're using something like even Git 2 has some Git 2 app dependencies. So you need to make sure that your Docker file is right. You need to make sure caching is right. Usually you do something called distro.x where you copy site packages and all of those things, right? So you have lots of layers where images are very big. So that essentially reduces its feasibility for function as a service. Because if I have one port for one function, my memory usage will shoot up. It will like take 100 MB for one function, which is not acceptable. So, and also it will take a long time to start, because even in the best case scenario, pulling 200 MB is not a quick thing, right? But on the other hand, these languages have a superpower, which is dynamic loading, essentially. So if you look at, I think this is not visible. Maybe we go. So if you see, this is again some ChatGPT pseudocode, it's just simulated. But you have this thing called import load, right? So if you have a function code that's coming from Git, the pod, the runtime, can just clone that code and import it on the fly. So you don't really need to build images for every function. So all I'm doing is for every project, I have one pod for all of these languages, and then we just import the code on the fly. So that makes it feasible to be in a function as a service. But it's not true scale down to 0, because even if like 10 of my functions are not receiving any requests, one of them is the pod is running. Whereas in Go, it will actually scale down to 0. But it's the best of both worlds, because you can load stuff quickly. There are many gotchas around this, like importative invalidated cache is something, like in my previous work we used to do this a lot, and sometimes when the cache is not invalidated, it changes wouldn't reflect. So that also causes lots of issues. So yeah, that is the dynamic language part. Yeah, this is the play this. Alright, so operator, this is the main thing which makes the magic happen. So far, if you think about it, PubSub is common, HTTP is common, database, UI, all this thing. This is the magic part. So Kubernetes operators, like how many of you have worked with KAs here? Okay. So you have this thing called custom resource definition, CRDs, where you can essentially define a type of your role. So see, if you look at it here, instead of like instead of istio, I have API version as my agent, and under that I have kind function. This is not a KX YAML. This is a custom KX YAML that I created. All it has is the name, the project, the language. So it's very minimal, but it has more stuff. This is just a demo. So if you look here, it's not clear.
Video I can't see.
Yeah, maybe pause once. I just go through. So I just read it out, it's not visible. So this is like K describe function 1, or it is done as previous slide. Oh, I think the zoom sometimes breaks here.
It went into Vim mode.
Okay.
Is it this?
Yeah. I just read it out. Yeah. So here already is added K describe function, which was just listed in the whole connection thing. So here, these are the main things, right? So I have two flags here, async is active, right? So by default, when I create a function, is active is set to false. So this function is false, and we have other information like name and all. And there's another thing here, deprovision time. This is not set yet. Okay. So yeah, I think resume the video. Here what I'm trying to do is I'm just doing get deployment grep hey. There are no deployments called hey. Doing get service grep hey. There are no services called hey. Right? So right now there's nothing running for my function. But then I go and send traffic. Right? I just send a request. So initially it didn't find it, but it immediately spinned up a pod for me. Right? That is the lambda function. So what happened essentially is when I call the request, my ingester it used the KX API to check if a resource exists of this name and if the active status is false. It's false, so it's set it to true. The moment that was set to true, my operator reconciled, okay, this is now active, so I need to start deployment for it. So you started a deployment, it created a service, you can create ingress, anything that you want. Operator is like, the reason it's called an operator is because if I am operating K8, I'm creating these resources, the operator is doing that for you. And all of this is pure code. So if you look at it here, we have this keep warm duration, which is default 5 minutes. So the moment I send one request, my bot will be active for 5 minutes, right? And that's how it works. And after 5 minutes, if there's no traffic, it will kill the bot. There's a cleanup job running, which is clean up the bot. And if request comes, it just extends by 5 more minutes. That's the gist of it. So yeah, and this deprovision time, I'm just trying to spell it. Yeah, deprovision time is set to 5 minutes from when it was created. So here I'm getting a response from the function, here is from go, and if I wait for 5 minutes, which will probably return that, and the function pods will go away. And yeah, I think here I'm showing is I call it time what is changed. So it was 1350, here it is 1355. So yeah, that's it. I'm just showing the code. All this code is linked in the QR code, and I could probably give the link of the repo as well. So yeah, that is how. Cool. So that is it. How much of the video is there? I think skip to around here. Just waiting for 5 minutes to pass. Yeah. So now the cleanup job is ran, and it basically has deleted the form. So right now, I can do magic time, and after 5 minutes of skip, the deprovision time has happened. Oh, I have you see that happened there. 1351 has happened, and the cleanup has just run, and would have deleted the deployment. Basically, it just marks it as inactive, and the operator again deletes the stuff. So that is the operator. Writing an operator is not that hard. There's a framework called QBuilder, it's by 8 guys and such. So it gives everything is like scaffolded. You just write this one function, which is called reconcile, where you just interact with the KS API to stuff. That's all you do. Yeah, the code is gone, and that's how litefunctions operates. Cool. Yeah, so this is like a thing, it's just dealing with the KS state, which is actually, and the KS API server to do what it needs to. So you get function, check is active, if it's not active, then release the deployment, if it's active, then create a deployment, patch the deprovision time. You're just working with the KS resources. Yeah, that's all. Cool, next. So yeah, this is all packaged in the head chart. So right from the wiki, version control, the database. So this head chart includes punchy operator, which is I really go this thing. Yeah, the speaker is operator. So it includes all of that in the chart. You can install it here. That's perfect. Yeah. So what next? This is functional right now. You can actually like use it. I think I just not even like probably audible. Audible, right? And done it. Few slides to go. Yeah. So the thing is working. So one stark difference, if some of you are aware of how AWS Lambda actually works versus this implementation, is I'm using containers, whereas Lambda uses this thing called Firecracker, which is a macro VM thing. It's supposed to be more secure, but it's very hard to work with, and the startup time is very high. It needs AWS research to get it to, functional state. That's probably something next you can look at. Right now, it's just containers. Containers are great, fast startup, great developer experience, everything. But only problem is the kernel is shared. So if there is any vulnerability in one of the function, and everything is gone. That's the issue. Yeah, micro VMs is something to look at. And unikernels is a very interesting thing. I just heard about it in the podcast. Essentially, what happens with unikernels is, so right now we do Docker images. We start with Linux, we install our dependencies, we run our code, right? Unikernels, it doesn't have Linux, it doesn't have an operating system. It basically, like my code, if you think about the function, all it needs to do is interop with the database and do some network. That's all it needs from the operating system. It doesn't need any other features from the OS. So you can just ship those and just work with it. It's a very new thing. There's one company called Nanos, you can look it up, which does that. But yeah, that's something I just put as research. Okay, yeah, I just had AI create some issues. There are some 22 issues right now. So if there's some Python and Rust, and the runtime